Hello everybody and welcome to my classroom. Today we will be applying the 4 glass laws to solve some problems involving changing gases. Feel free to print out this presentation and work through the problems along with me. Or pause the video to work them out on your own and then follow along with me to check your answers. Let's get started. A sealed balloon swells from 10 liters to 35 liters when it moves from a colder room with a temperature of 10 degrees Celsius. What is the temperature in the new room? First, we need to determine which of the gas laws we need to apply to this case. To do that, I first want to identify the constant and changing variables. To do this, we need to look for keywords in the problem. For instance, sealed tells us that none of the gas has escaped or been added. This means that the number of moles are held constant. You might want to say the volume is constant, but not in this case since the housed container is flexible. It's a balloon. The other keyword is room. This means that we have not changed locations dramatically. We have merely walked down the hall, which means the pressure is constant. It also does not say it changed, so it is safe to assume that it's constant. This means that P and N are constant, while V and T are changing. This means we need to use Charles' law. Let's look at the variables we need to solve to fill in Charles' equation. First, the initial volume is 10 liters. The initial temperature is 10 degrees Celsius, the final volume is 35 liters, and the final temperature is what we're looking for. We need to check to make sure our variables are in the correct units or at least consistent. Both of the volume values are in liters, so we're good there. However, the temperature is in Celsius, which can't be used with the gas law equations. Thus, we are going to need to convert the value to Kelvin. To do this, we need to add 273 to get a temperature of 283 Kelvin. Now it's time to plug these values into our gas equation. We need to isolate X, the unknown temperature we are interested in, by cross-multiplying and then dividing by 10. This gives us a temperature of 990 Kelvin, or 0.5 Kelvin. Remember that the units of your answer will be the same as the units provided in the equation. Since the temperature we used was in Kelvin, then our answer is in Kelvin. If we needed to convert this to Celsius, we would add 273 to get 717.5 degrees Celsius. Pay attention to significant figures. Since this is a mixed operation problem, the temperature conversion was addition or subtraction. The significant figures should be used in your answer should follow addition and subtraction rules, which would be the least decimal places. That is 1 in this case. Let's try another one. 0.25 moles of oxygen gas at STP occupies 5.60 liters. How many moles of oxygen gas occupies 30 liters of volume? We again need to identify the constant and changing variables. The keyword in this case is STP, which means standard temperature and pressure. This means that the temperature and pressure are constant, while the number of moles of volume are changing. That means we need to use Avogadro's law. Let's figure out the values we need to complete the equation. The initial volume is 5.60 liters. The initial number of moles is 0.25. The final volume is 30 liters, and we're looking for the final mole amount. All the variables are inconsistent units, so we are good to start substituting the values for the variables in the equation. Next, we need to isolate X by cross multiplying. Then dividing by 5.60, this results in a value of 1.33928 moles. Now, all we need to do is round based on significant figures. Unfortunately, I've already showed you. But since this is all division and multiplication, we round to the least number of significant figures, which is 3 for this problem. Thus, our final answer is 1.34 moles of oxygen gas. 2 more to go. A sealed tank drops in temperature from 30 degrees Celsius to 5 degrees Celsius. If the new pressure is 0.6 atmospheres, calculate the original pressure in kPa, or kilopascals. Again, we need to identify the variables. The keyword in this problem is sealed. This means that the amount of gas is not changing. It also means the volume is constant since this time the container does not have flexible sides. It's a tank. Therefore, N and V are constant while T and P are changing. This is an example of Gay-Lussac's law. Now, let's identify the variables that we need to use in place of the equation. The initial pressure is what we're looking for. The initial temperature is 30 degrees Celsius, the final pressure is 0.6 atmospheres, and the final temperature is 5 degrees Celsius. Now we need to check our units. First, the temperature values are in Celsius, so we need to convert them by adding 273. That results in a temperature of 303 Kelvin and 278 Kelvin. Second, the problem asks for the final pressure in kPa, or kilopascals. Thus, we need to convert the units. But we can either convert now or in the end. I'm going to wait to the end. Now, to replace the variables with their corresponding values. And now to isolate x, we need to cross multiply and then divide by 278 to get a pressure of 0.6539 atmospheres. Now this is in atmospheres because the final pressure used was in atmospheres. Thus, we need to convert this to kPa, like the problem requested, by multiplying by 101.325, since 1 atmosphere is equal to 101.325 kilopascals. That gives us a final pressure of 66.3 kilopascals. Rounded to the 10th place because of the mixed operations in the problem. Last one. A 700 millimeter mercury sample of gas occupies 50 milliliters. Calculate the volume when the pressure drops to 0.8 atmospheres. As always, we need to identify the variables. This problem only references pressure and volume. Thus, it can be assumed that the temperature and moles, T and N, are constant while P and V are changing. This means we need to use our last law, Boyle's. Let's see if we can identify the necessary variables to use Boyle's law. First, the initial pressure is 700 millimeters of mercury. The initial volume is 50 milliliters, the final pressure is 0.8 atmospheres, and the final volume is what we're looking for. In this problem, the variable units are inconsistent. I can't have two different units for pressure. Thus, I need to choose one to convert to. I'm going to convert atmospheres to millimeters of mercury, but it wouldn't matter which one I chose. Try to convert to atmospheres and see if you get the same answer. Thus, I need to multiply the final pressure by 760 millimeters of mercury, since 1 atmosphere is equal to 760 millimeters of mercury. This gives me a pressure of 608 millimeters of mercury. Now we are ready to replace the variables in the equation. We isolate x by dividing by 608 to get a value of 57.565 milliliters. We need to take into account significant figures. Since this was all division and multiplication, it would be the least number, which is 3 in this case. Thus, the final answer would be 57.6 milliliters. Excellent work! You have just applied all 4 of the big gas laws to solve problems. Check out my next video on the combined gas law and some other challenging problems. Always remember to read the problems carefully and identify the keywords you need to help solve it. Thanks for tuning in.